Okay, shall we start? Okay. All right. Do you want to say something, or can I just go ahead? Okay, great. So welcome everyone. Welcome to the SBI tutorial. And yeah, this will be a hands-on introduction to simulation-based inference. And we're gonna work with a case study from ecological monitoring with limited data. My name is Jan, and I'm from the Transfer Lab, Applied AI Institute for Europe. And I also have my colleagues Christoph and Janos with me here today. So in case you have any questions later on, you can also raise your hand and they can help you. And in general, I really encourage you to be interactive. We are not so many people today, so it's good for you. And as soon as you have any problems or questions, just raise your hand, and then we can sort this out. And I will now give a brief introduction to the tutorial, like to the content and so on. And then we will have some time for the setup as well. But I want to mention already that all the materials are available on GitHub. There's also a link in the abstract on the USIPy schedule. And yeah, but we will have time for the setup later. Okay, so I'm quite happy because I found this actual problem and that is related to, or that can be addressed with simulation-based inference. And it's how I call this now, conversation crisis in Poland. Because as in many other places in Europe, there has been some initiatives to kind of support the population of wolves in the forests, and now here and there are more and more wolves, and they also start to attack the livestock or the domestic animals, and that's a problem, of course, because the farmers are angry, or their sheep are attacked by wolves. So, for example, I found this news report that there's a problem with wolves here south of Krakow, and so farmers are appealing for culling of wolves, actually. And there's also more recent research on that. So there's a paper in Animal Science and Genetics, kind of a preliminary report on wolf attacks on flocks of sheep and native breeds in Poland. So that's actually a real problem. And it's a nice use case because one usually uses simulators to model the dynamics of populations and environments. And it's a very concrete use case where we can apply simulation-based inference. So for today, I would like you to imagine that you are consulting the State Environmental Agency in Poland for this problem. Right, so the problem is that we have this dilemma that wolves are recovering after, they have been nearly extinct, but now they're recovering, and yeah, on the other hand, the farmers are losing livestock. So the policy question that we kind of have to address is how much culling, how many wolves should we shoot, basically. And that's our scenario for today. And we're going to be using a simulator that is kind of a classic model in ecological modeling. It's called the Lotka-Volterra model, and it's a classic model for predator-prey dynamics. So I'm going to quickly explain these equations, two differential equations. We have two populations. The X population is the deers, and the Y population is the wolves. And then we have this typical dynamics that the deers, they have some birth rate, so they grow with this birth rate, the population of deers, and the population reduces with some predation rate. So how many wolves are, how many deers are eaten by wolves. And similarly, the wolves, with the variable Y, they have some efficiency, how much they reproduce, and some death rate. And these two equations, they describe these oscillating dynamics of these two populations. And I'm choosing this model because it's kind of well understood. It's a classical model. It has these oscillations, and it's nice because these parameters map to real, like physical, or like the parameters have a really nice interpretation. And it's good for SPI because it's really fast to simulate on the one hand. On the other hand, it does not have a likelihood function, so we cannot use classical Bayesian methods. So the central question is, how can we infer parameters given observations? So if we now obtain some data from the farmers or from the state agency, and we want to apply, or we want to fit the Lotka-Volterra model to these observations, how do we find the parameters to then be able to model the dynamics and help the agency to make a political decision? And now, the traditional approach could be to use some kind of optimization. So we try to optimize the parameters such that they can reproduce the observed number of wolves and deer. Right, so we would try to find the best parameters. We would use some optimization strategy or some optimization algorithm. We put in our simulator that can simulate some wolf and deer dynamics, and we put in our observed data, and then we try to match them. And for example, we would then find this one location in parameter space where we can really reproduce the observed number of wolves and deers, and that would be one parameter combination of these 4 parameters of the Lotka-Volterra model. So some kind of rate for the deers, and some predation rate, some efficiency of the wolves, and some death rate of the wolves. So this would give us an answer, but there are several problems with that. So we don't have, in this case, we wouldn't have like a principled way to estimate the uncertainty that we have, because we have limited data. We might have some parameter uncertainty. And another problem is that because we only have one solution, we might miss alternative solutions as well. So it could be that we run this optimization algorithms several times, and we get, say, like 3 different parameter combinations that all kind of explain our data. And that is difficult to decide which one we take. And now one of the central themes here is for today is that we want to estimate a distribution over parameters. So we want to perform Bayesian inference. Not just a single point estimate, but a distribution over parameters. And this distribution is usually called the posterior distribution. So instead of just having one single estimate that can explain our data, we have a distribution with some uncertainty, some variance, and we can even look at the correlations between different parameters, and we can then make more informed or more robust decisions. So we're always going to be looking at this distribution over the parameters conditioned on the observation. And then, so maybe quick show of hands, who has been working with Bayesian inference, or who knows about what a likelihood is, what a posterior is. Okay, that's good. So in general, in Bayesian inference, there's a central theorem, or the central rule called Bayes' rule, so our goal is to obtain this quantity, the posterior distribution. So that's the distribution over the parameters conditioned on the data, because then we can say, okay, given these observations, we have these parameters and this uncertainty, and then we can make some decisions. But this mathematical quantity is usually a bit difficult to obtain, but there's this rule saying that we have the likelihood, which is the distribution over the data conditioned on one parameter set, and the prior, which is our initial assumptions about the parameters, maybe some boundaries within which these parameters have to lie. So for example, for these rates in the Lotka-Volterra model, most of these parameters should be, all the parameters should be positive, right? Because they're rates, for example. And then Bayes' rule says that we can just multiply together these two distributions, the prior, our initial assumptions, and the likelihood, and then we can obtain the posterior distribution. And this is a very central rule, but there are lots of algorithms to do this, like Markov-Chain-Monte-Carlo sampling, variational inference, and lots of tools developed in like the 60s, 70s, and later. These are like classical methods to perform Bayesian inference. Now the problem with our simulators is that we cannot apply these algorithms, because the simulator is kind of a black box. We don't have, most of the time, don't have access to the likelihood, so we cannot evaluate this mathematical form of the likelihood. Or in some cases, we kind of have access, but it's too slow. So for most simulators, scientific simulators, we cannot use MCMC or variational inference. It just doesn't work. And this is where simulation-based inference comes in. And this is a rather young field, so maybe 5 or 10 years old. Because since then we have methods, or like we have new network-based methods that can perform inference for us. So instead of using these classical algorithms like MCMC, we train neural networks to perform Bayesian inference. And here the idea is, in like a pseudocode, we sample parameters from the prior. So the prior distribution we can just define, so we can easily sample from that. And then we put these parameters that we sample from the prior into the simulator and generate lots of simulated data. And this constitutes our training data set. So we have parameters and data that match to each other, like pairs of theta and pairs of parameters theta and data x. And then we can train a new network on this training data set in a supervised way. And then we can, so up to here we only have used simulated data. And then afterwards, after training, we can put in our observed data and obtain the procedure. That's kind of the idea. And for this process, we don't need a likelihood, because we only sample from the simulator. We only run the simulator forward. And in principle, this works with any simulator if the simulator is fast enough. So if we can generate thousands or millions of simulations. Okay, this was like a really brief introduction to simulation-based inference. And for today, the plan would be to have 3 exercises. The first one is just like a really first exercise on performing simulation-based inference on this log-Valterra example once. The second one is more like how can we actually check that the inference worked correctly. And in the third exercise, you can actually apply this to your own simulator in case you have brought one, or I have 2 other simulator examples where you can apply the same workflow again. Okay, and then we're going to be using this Python package called SBI, which implements all these methods and like all the utilities that you use to perform these methods. All right, are there any questions so far before we go to the setup? Yes, please.
Yeah, so when you train your network to learn the state distribution, do you use some parameterized family, or do you, how
yes.
do you model this?
We're gonna have a bit more detail about SBI, like how it actually works in a moment. But that's a really good question. So I will try to address this question in a couple of slides. No more questions? Okay. Then we move on to kind of a bit more depth on how actually SBI works. As I said, this is kind of actually this field is a bit older because there are these classical SBI methods that have been developed in like the 80s or so, and there's the modern version of these methods that have been developed like 10 or 5 years ago. And the classical approach to simulation as inference, it's really rejection sampling. And let's have a look at this. And here the idea is that we just perform rejection sampling. So we sample from the prior, we simulate some data, and then we compare the simulated data to the observed data. And if it's really close, we accept the sample, and otherwise we reject it again. And in code, this looks like this. We have okay, maybe this can be done more efficiently, but we have a for loop. We sample from the prior, we put the sample parameters into the simulator, and we get some simulated data. And then we have some distance metric that we have to define, and some acceptance threshold epsilon that we also have to define. And then if it's below, then we append it to the list of accepted samples or accepted parameters, and we do this like as often as possible. And then the posterior samples, so the approximate posterior, is just this bag of samples that we have accepted. Kind of try to get all the parameters that can reproduce the observed data with some epsilon. That's all. That's kind of the idea of rejection sampling. Now, this was a good idea, but of course this has some problems in higher dimensions. So if we do it in 2D, then in order to obtain 1,000 posterior samples, we simulate 10,000 times and accept 10%. But if we move to 5D, to get 1,000 samples, we already have to simulate 1 million times. And then as we move up with the number of dimensions in the parameter space or in the data space, this quickly explodes, just because of the curse of dimensionality. And it also has other problems, because we have to define this distance metric, we also have to choose the epsilon, and so on. Now, the modern way to do this is that we actually try to learn this mapping. Like we learn this function that defines the mapping from data to the distribution over the data, over the parameters. Because in rejection sampling we just do that, the sampling approach, but here we actually learn the mapping. We have the mapping from parameters to data, the simulator, and this mapping we want to invert. We want to get the mapping from data to the parameters. And for this, we perform neural density estimation. So as I said before, we have this, we generate our training data, and then so pairs of theta and x, and then we have some loss function on the parametric family, that like a family of distributions that we optimize, and then this new network that represents this family of distributions can be evaluated at our observed data, and then we get the posterior. And just to get to form some intuition how it can actually look like, so this neural density estimator, what is this actually? What kind of object are we learning? The very simple approach would be that we assume that the posterior is just a normal, like just a Gaussian distribution. So then this new network would have to learn a mapping from the data that we simulate or observe to the mean and the variance of this Gaussian. So we can put in data and we get back a mean and a variance, and this would be our approximation to the posterior. That's like quite intuitive. The next step, but it's not really flexible, right? So this assumption of the Gaussian posterior is just too strong, but we can also use a mixture of Gaussians. So then the new network would have to have in the output layer several means and the covariance matrix and the mixture weights for the mixture of Gaussians, and that's what we learn. So we put in data, we get back all the parameters that we need to define a mixture of Gaussians, and this mixture of Gaussians would be our approximation to the posterior. This already works quite well, but since a couple of years ago, there are now these models called normalizing flows that are even more flexible or easier to train than a mixture of Gaussians. And that's nowadays default to parametric family to approximate the posterior.
Excuse me.
Yes.
But does this mean that your solution has always have to have this kind of single distributed peak and stuff? So you don't have like multiple peak solutions and things like that? Or?
Yeah, good question. So the question is, does this mean that the posterior really has to be unimodal? And yes, for this first case, that would be the assumption. If we assume that the posterior is Gaussian, it has to be a unimodal shape. But as soon as we move to more complex models, so if we use a mixture of Gaussians as our parametric family, then we can have multimodal posteriors as well. And especially for normalizing flows, they're really good in learning complex shaped posteriors or distributions in general. Okay.
Sorry.
Yes.
Could you please elaborate a bit more on the first step, maybe on some examples, like how that generating those training pairs would look like in practice?
Yes, so to generate the training data, you have to define a prior for your simulator, so using domain knowledge. So for the Dr. Valterra that we see in a moment, we just have to define some parameter ranges that are plausible, like overall, and then we sample from this prior. So we define a uniform or some tractable distribution. We sample from the prior, and for each parameter that we sample from the prior, we simulate using our simulator. And that's everything. That's all we need to do. That's our training data set. Okay, and then the cool thing about these neural network-based approaches is that we can, like after training, we can just perform inference for new data basically instantly, because we only have to do one forward pass to the network, and we get our posterior estimate. Yeah, another summary. So these are the 3 steps. We generate training data, then we train the neural network, and then we can get the posterior instantly. And this is called amortized inference, right? Because this initial cost of generating all this training data and training the neural network kind of amortizes, because we can now perform inference from many different observations really fast, so kind of for free. And if we compare this to traditional, or like to actual classical Bayesian inference methods, that's actually one advantage compared to MTMC. Because for MTMC, even so we have the likelihood, we can perform all these MTMC sampling steps, but we have to do this for every new observation. So we have to run the MTMC chain for like a couple of minutes or hours. But for neural posterior estimation, for SPI, it's just one forward pass in the neural network and we get the posterior. Okay, that's with the theory, and now we can get more hands-on. But before, I want to make sure that everyone has the setup. Everyone who wants to do the exercises should. Let me show the repository. So that's the repository. Does everyone have access to the repository? That's good. And then, it's really simple. Using UV, you can install UV using this command. Then you clone the repository, you cd into it, and then you should create a virtual environment, and then activate it, and then call UV pip install -e dot, and then it should install all the dependencies. And of course, I really want to make sure that everyone has this. So please raise your hand if you are not able to execute this test command here. Or does anyone need help with the installation?
Is it also possible to run this in Colab directly?
I have not set up a Colab, unfortunately, no.
But if I just do the manual pip installs for the libraries you have here, should be fine, right, in Colab?
So it depends a bit on the dependencies, right? So if you have SPI installed, here we have this list of the core dependencies for this tutorial.
Because it's a project, you can maybe pip install git plus HTTPS the repo.
Okay. Thanks.
It's not pip-based, it's UV-based. It's not work. There's no requirements, right?
There's no requirements,
I don't know if it's work, if you have to find it in the project tunnel or if it takes you the log, I guess not. Can you call pip?
But so I think maybe you're so if you really I think the easiest way would be to just clone it, but it's not possible for you.
Possible, just have a vanilla environment, so install all the stuff on laptop.
Yeah,
Your laptop. That's why.
So
So you need to install all the basic stuff. But yeah, I will do that.
Okay.
Just download.
And the cloning might take like 1 minute or so because I have pushed the pre-trained models as backup and also the slides, which are a bit bigger.
I go on hotspot, like me, or what's the
The Wi-Fi.
Wi-Fi? Yeah.
Okay, let's just wait for a couple of minutes, then everyone can participate. I was just thinking that maybe it's good to have some. Can you hear me without mic? Is it okay?
Yeah, but
Okay.
the people on the stream.
There are people on the stream. Okay. Thanks. Okay. Just to give you some intuition about, in case you have not heard about the Lotka-Volterra model, and I noticed that I don't have these plots in the beginning of the notebook. So just to show you, to give some intuition about how this model actually works. So we have on the x-axis we have the time in days, for example, and then we have a number of agents for each population, and we have this typical dynamics. So we have the prey. It has some starting number, and then the predator as well. And as the predator enters the environment, like a wolf, they eat the prey and then they reproduce, and then at some point there are not so many preys anymore, so the wolves die again, and then we have this typical first, like the sheep or the deer, they reproduce again, and then the wolf come in and they eat again, and they have this typical oscillations of the two populations. And now you're using this model to simulate or to kind of understand the dynamics that happen here in south of Krakau. And just to give you this intuition. And I think now everyone has the installation working, and we can start. Okay, cool. And then now the idea is that we perform neural posterior estimation. So the modern SPI version, we apply it to this Lotka-Volterra model to understand the dynamics. And if we look at the notebook, kind of the story is that as it is, we don't, so the hunters and farmers, they have collected some data points, so they have counted the wolves and the deer in the environment, but the agency, they don't give you the entire data set. They just give you summary sets, summary statistics. So you don't have the time series for each day. You only have some summary statistics like the mean and variance and the skew of the distribution and the maximum of the distribution. And that's the observed data that you have. Because due to some privacy constraints, whatever, you don't have the full data, but only this summary statistics. So now I will just do the beginning of the notebook with you together, and then we have some time for you to work on this on your own. So we do the imports, and then here we set the number of simulations that we want to use, and also have this variable called number of workers. Depending on your laptop or on your system, you might want to reduce this number, but it's kind of the number of workers that you can apply to run simulations in parallel. So that's something we have to set in the beginning, and then also we have this flag here that I set to false for now. We can try it out later with true, but it's just an extended version of summary statistics. So we use some additional features, but for now, let's use it with false, just to see what happens. And then we have to do some preparation of the simulator. And actually we get our observed data. So this is the data that we get from the agency, and here we can see what it contains. Right? So that's all we got. We're given the data set of the farmers, that is actually a time series. We only have these summaries, so the mean of the deer population, the standard deviation, the maximum, the skew, the kurtosis, and the same for the wolf. So 10 summary stats in total. And then the next step is that we define the prior. In this case, we just use a uniform prior over these 4 blot coverture parameters.
You don't provide some kind of Fourier transform of the values over time to see the periodicity?
Yeah, that's a good point. That's if we do some feature engineering, that's obviously one thing to do, and we do this later on with the autocorrelations in a way. But I wanted to construct this case where we only have these like few numbers, just to see how the posterior looks like in that case and how we can improve it later on. Okay, so we have this convenience function that gives us the prior, and then if we sample from the prior, we get just some kind of random combination of parameters for our training data set, and we can now plug these parameters into our simulator to generate the corresponding data to generate our training data set. And let's go to this up to this point together. And now from here on, I would ask you to just go over the notebook, read through the lines carefully, what is happening, and execute the cells. And if you have any questions, if you need any explanations, let me know. And let's say we have 10 more minutes for that, and then we see how far we get. Okay? Great. So, yeah, as I said, as soon as you have any problems, let me know. Let us know, then we can work directly.
The fact mine is not working. It seems that it's a problem with the tensors.
Okay, let me have a look. 10 parallel CPU cores. Just one is
Oh, which is completely wrong.
and then now it will probably take that long to generate the simulation. If you just have a look at this so here we are calling which is just a Bayesian function here. Give it estimator prior to the number of observations that you want. And it will run all observations in parallel. And then you get back the time of X.
Internal, like, perspectives.
Okay, but this is still under
Can you show me the resolution?
Probably will take 1 or 2 minutes for running all these like 10,000
Problem because
the top one, right?
much platform
Anyone else with errors or problems?
Oh, you can run it up and down.
It's pretty old.
Yeah, I guess so. Yeah. The problem is torch. So
Doesn't work in general with lots of new tools.
no, the problem is like the torch. Torch isn't working with your Windows. That's the problem.
Yeah, but my question is, it's like if I just try to, because I also have access to a few union servers.
Yeah.
So I have a few environments that are very Torch working. So can I just install them to all the
Yeah.
issues working as well?
Yeah.
Just trying to do.
So you can use the PIP interface of your Wii to install into the environment. I think you have to check. I think you have to give like flag to
The video problem is I'm not sure it will serve as the use content.
Oh yeah, okay. But you can install to Conda by PIP, right? So that's no problem. I think this guy has no Conda distribution. That's not Conda distribution, right? This guy.
Yeah, but
It has.
install,
Yes,
Yeah.
yeah.
Pip install on top of it.
Yeah.
It's not very clean, right? But,
Well,
should work.
Yes.
Is 3.10 now?
yeah.
Okay.
Try.
Very good.
You might assume she was the way around.
as you like. Let's say because there are some problems coming.
Oh, that reminds me more.
Yeah. This, what I mean,
Trying to
the
understand
server, the truth is still running like not. Just for the yeah. So
so you're not using the UV installation, but you have your own random setup.
Yeah, I can just try to do it. Let me try to do it this way. Try to install it with
Sometimes it has problems. Yes.
Or that's with
This one is, I mean, at least in VS Code it works. VS Code is
yeah.
because this is also like my, I have a direction for this environment, so it already but it works in VS Code, so maybe I will keep it.
Yeah, installation. Yeah. But yeah, but it successfully. The simulation was successful. Yeah. Okay. Yeah. Okay, but what is your installation setup? So locally, have you cloned? Oh, have you cloned the virtual repository?
This is already had installed the Windows subsystem.
You mean
The Windows?
And where does it start?
But you can try this.
On the
from
front?
no from Icon.
let's try it.
So using Conda, yeah.
Because the other kernel
Oh yeah, there's a specific bug for the crypto version. Can you install pip install tradelets? Tradelets? No.
Okay. Can you maybe you can try to do it with UV? UV is package management. If you go to the you have cloned it with UV, right? So you have it with UV. Yes. Yeah, that's
No, that's okay.
That's okay.
This one.
Yeah, and have you used UV before?
No,
Not
well,
really.
actually instructions.
Yeah. So it's if you go to the and just copy the first line to this one. So if you follow, if Donald finishes, then you should already have this done. Yeah. And then you just and then the install. And it's completely
Yes.
and then once you're done with that, you would just do the notebook and it will open. And then so that's everything.
Soll ich dann tun oder was meinst du?
The training so, but yeah, so few simulations.
Yeah.
10K.
So, network operations only use and then it's comparing distribution.
The conditional distribution. So you give it
Yeah.
samples from the joint, from the
Yeah, this is about.
and it has
this is
a
about
conditional.
just fixed.
But then
notebook
you use this to
6.5 something, but this
I
is
don't know
not
if there's any
compatible with SPI, which is about 4.6.4.
without
So,
like that you can sample distribution.
we want to
Like the system applications.
Other domains.
Yeah.
so
Because it seems super useful, like all the time, where like simply, you know,
Yeah, of course. I mean, these methods
from
from samples.
from theory.
Totally. Like all these methods, SPI is built on kind of the classical conditional condensed expression. So all like image generation and so on, like diffusion models.
Oh yeah.
I mean, diffusion models are used to generate images by learning simulation, by learning distributions, right? So they learn the distribution of pixels, and SPI just takes this method from classical machine learning and applies them to simulations.
Yeah.
So, yeah, the question is.
But I guess this is maybe easier than
Right. So
Yeah, I mean,
Yeah, yeah.
This
Distributions of images are way more high.
for some reason it doesn't work.
I see. Okay, so maybe you should be okay. So, okay. So just
Okay.
So I have a question.
Yes.
Is the initial conditions they are fixed because they are not part of the conditions?
The initial conditions for this local return.
Yeah.
Yes, they are just hard coded somewhere in
You
the.
fix them arbitrarily or?
Not arbitrarily, so they, but yeah, so they, I think it's 40 deer and 9 wolves, but it's, we could use other initial conditions. Yeah.
But they are not part of the observed data, it's you.
No, it's,
That's
I mean, the whole, I just like this example because it's kind of
yeah.
recent, but everything is kind of made up still.
Yeah.
What options used in this case? Is this just mixture Gaussian or?
This is, the default is normalizing flow, so mask autoregressive flow. Okay, so let's quickly go over the notebook. So I've seen that some of you had problems with the installation setup. That's unfortunate, but we have to move on. And I just want to go over this code. So this is really SPI in 5 times the code. So we first have to define the method. So we discussed neural posterior estimation. So this MPE, but there are other methods. But this MPE is like a good default choice. Then we call this convenience function from SPI. So this is called simulate for SPI. We could just give it to the simulator, the prior, or the distribution that you want to simulate from, and the number of simulations, and the number of workers, and then it will simulate for you in parallel the training data set. Then we append the simulations to the MPE object and call train, and it will run the training with all the defaults that have been set in the SPI package. And then after training, we just have to call build posterior on this MPE object, and we get our posterior object. And now this posterior object is, like, under the hood is a neural network that we can give it observed data, and it will give us a distribution condition on this data. And that's what we do in the next line. So we can treat this posterior distribution just like a PyTorch distribution. So we can call a sample, the number of samples, and then we can pass it the observed data that we got from the farmers, and we get the posterior samples. And okay, we save this object file just to use it in a second notebook. But the next step would be to visualize the results. And And because the model has 4 parameters, we have this 4-dimensional distribution. And of course, the 4-dimensional distribution is difficult to visualize in 2D. So there are these typical plots called pair plot or corner plot, where we just visualize on the diagonal here, we visualize the 1-dimensional marginals for each parameter, the 1-dimensional distribution for this parameter. So everything collapsed onto 1 dimension. And on the upper diagonal, we visualize the 2-dimensional marginals for each pair of parameters. So for example, here between alpha and beta, we have this 2D distribution, and for all other pairs as well. And this is actually, this is the posterior object that we wanted to obtain. We now have an estimate of the parameters given the data. So we can say, so the red line shows the actual true parameter that we have in this case, because everything is simulated. In practice, we would not have these 2 parameters, but the posterior shows our estimate and our uncertainty that we have for this observed data. And then we can calculate some statistics on this parameter, on this posterior distribution. So, and I think this is really important to understand, like in contrast to optimization. Okay, in optimization we could run like 100 optimizations and then look at some averages or some standard deviations. But here the posterior is really a mathematical object that gives like guaranteed uncertainty estimates and so on. So we can look at these statistics. We have a mean and a standard deviation estimate of our parameters. And then we can, for example, look whether our true parameters, just as a test, whether our true parameters lie in the 95% confidence interval of the posterior, which is the case in our setup here. But importantly, we can also look at the correlations of these parameters. Right? So we can look at each pair of parameters and do a correlation. And here we can see that there's actually very strong correlations between the parameters. And what does this actually mean? This means that we have like many different parameter combinations that can explain our data, because there are some compensation mechanisms. Right? So if we look at the parameter of the pair between alpha and beta, these 2 marginal distributions are really broad. So meaning that they are that we are very uncertain about these parameters. But that's only because there's a very strong correlation between the parameters. So as soon as we observe different data, to formulate it differently, if we change the beta parameter, like if we increase it, in order to observe the same data, we would have to increase alpha as well, because they are very correlated. So they can, like an increase in beta can be compensated by an increase in alpha. And so this is just in terms of the parameters. So if we look at the interpretation of the log-Volterra model, so if you look again at the parameter names, so alpha is the deer birth rate, and beta is the predation rate, right? And this kind of makes sense. If we increase beta, so the predation rate, in order to observe the same data, we also have to increase the birth rate to compensate that, right? And this is these kind of insights that we can get if we have the full posterior. And that's the power of simulation-based inference, because with simulators we always have these interpretations of parameters, and now we can actually get this with posteriors. Okay. And another cool thing about this approach is that we only received observed data from the agency, so like a summary of the full data set. But we have our log-Volterra simulator, right? So we can plug in parameters and we get the full time series of the dynamics. And that's something we can do now. So we can just make predictions of how the populations evolve, given the data that we have observed, by just sampling from the posterior and then running the simulations on the full time series. So if we do this, we sample 1,000 parameters from the posterior, we simulate them. So these parameters have been conditioned on our observations. And then we can visualize the full Lotka-Volterra time series. And that's what we get. So over the days, we can see how, like, given our initial conditions and given the observed data that we have, this is how the populations will evolve. So that's actually something we can now show to the agency to make a political decision, right? We can see, given the current circumstances or given the current data, the roles will kind of increase and then decrease again and so on. And because we have a posterior with uncertainty estimates, we also get these uncertainty around our estimate. So we can see as time moves on, we get more and more uncertain about our estimate. Actually, I mean, actually this doesn't look so good, our prediction, right? So we are really uncertain after like 50 days. And that was my point to show, because the reason for this, for our kind of bad prediction, is that our summary statistics are not good. It's just like the first 5 moments, and these 5 moments don't tell us much about the dynamics of the time series. So we don't have time for this now, but a good exercise would be to now use better data, use better summary statistics. Like you proposed, we could use a frequency decomposition of the time series. What I did here is just use the autocorrelation, the first 5 legs of autocorrelation to capture the oscillation in the time series. And this is our additional summary. And then if we do this, then we get a much better estimate. Let us just do this quickly on my notebook here. So if we set this to true, and then run the thing again, now we can see that we have not only the 10 summary steps, but also we have these autocorrelation lags with different time steps. So the simulation is almost done. Did anyone try this out already? Okay, cool.
Those areas are close when the 90% credible interval, when our prediction is not even within this interval, it's like a numerical problem. What happens?
Yeah, I think the problem here is that we do the map estimate, so we don't take the mean. The mean should be in the center of the confidence interval, right? But if we do the map of the posterior, so we actually optimize, we go to the top of the posterior, which doesn't have to be the mean, then it could be outside. Yeah. So just a bit, I think around 220 or so is usually when it converges. So now we can already see the posterior looks different, right? Some of the correlations are gone because we have more information, so the posterior can be more constrained. Actually, this uncertainty that we have here is probably just due to the observation noise that we added in the simulator. And so if we do the prediction again, now we simulate data, we sample from the posterior given our observed data, and we display the full time series, and then this looks way better. So it's really a question, as always, like how you engineer the features. And in this case, yeah, this involves some actually us looking at the data and understanding the data and choosing the right summary stats. But in practice, we often have like way more high-dimensional data or like more complex time series. And the good thing is, because we're working with new networks, we can actually let the new network learn the summary statistics automatically, end to end. So if we have image data or time series data, for image data we could use in CNN, or like just append it in front of the density estimator, and the CNN would learn the image features. Or for time series, we could use the transformer to automatically learn these informative features from the data. So we don't have to do this in practice. This was just for the log example. Okay, so then let's go back to the slides.
Do you have some example with that fine-grained time series data?
Yes, we could. I mean, we have here time series data, right? So we, in principle, instead of handcrafting our summary stats, we could now use an embedding network like a transformer or an RNN. And these networks are actually also implemented in the SPI toolbox. So this would be straightforward to do. Just for this tutorial, I wanted to show this summary stats approach. But in principle, you could just take the embedding networks from SPI, from the package, and train them. Yeah. And we also, in the tutorial materials, we also have the other simulator called this SIR simulator for epidemiology modeling, which is also time series. Okay, let's do, the recap can be quick because we just went over the notebook. Just to summarize again, we performed the posterior estimation. These were kind of 4 steps. We observed data, so that's just what we got from the agency. Then we simulated our training data. We trained MPE, and we got the posterior. We didn't do any checks. We just give it our data, get the posterior, and we made some predictions. So this is cool. Now, but if we now go back to the agency and say, here are our posterior estimates, this is how it will evolve, and we recommend these decisions, then they will actually make political decisions. So they want to be sure, right? So and the whole approach of SPI is new network based and is based on limited data. So things can go wrong, and that's why we have to perform some diagnostics. And this is really important because if we have limited data or if we have data with limited information, these new network-based approaches can actually fail silently. So we might not notice if we don't check. Yes. So there are 3 sources: the new approximation itself. So the good thing is SPI has guarantees. So if we do the mathematical proofs, we can show that in the limit of unlimited training data, things converge to the actual posterior. Similar to MCMC, which has guarantees, but for MCMC we don't have this limited data thing, right? So there we can actually show it will converge to the equilibrium distribution, so things are fine. But for SPI, we have limited data, so it's not that straightforward. And then the data engineering problem, right, that we noticed already, but this we can solve with new networks and so on. And then also the problem of prior specification, or actually model misspecification as well. So it could be that our prior is too narrow, so that we cannot capture the observed data. And then if we do the training on simulations, everything looks fine, but then we apply the observed data, and this observed data is out of distribution. And then things can go completely wrong as well, because the new network will just extrapolate to this out of distribution, and anything can happen. So there are specific checks to make sure this doesn't happen. It's not so easy because, of course, in theory it would be nice to have kind of Bayesian reference priors or like less informative priors to not introduce any biases. But then, on the other hand, if usually in SPI we work with actual scientific problems where we have domain knowledge, and we really want to make sure to use this domain knowledge to constrain the parameter space that we search as much as we can. So usually we use uniform priors in certain bounds, because we know for sure, using domain knowledge, we know that the parameters should lie in this region. So actually, this concept of reference priors or uninformative priors is kind of not so common in SPI because it's more like a pragmatic approach because we want to use our domain knowledge. Yeah. Okay. So in summary, we have 4 different checks that we should perform. The first one is the prior predictive check that we should actually perform before we start the training. So we just simulate lots of data from the prior, and then we compare this data distribution, the prior predictive distribution, to our observed data. Right? So we just check whether the observed data is actually somewhere in our distribution of prior simulation data. And if not, then we have to change the prior somehow, or the model the simulator itself could be misspecified. That's the first check. Then we perform the training, and of course we can just reuse the data that we generated for the prior predictive check. We can reuse it for the training. So we perform the new network training, and then we can do the usual checks for new network training. So we look at the loss curves, at the training loss, at the validation loss, and look for any instabilities and so on. And the third check is after training, we do the posterior predictive check, similar to what we have done now. We sample parameters from the posterior, we simulate them, and then we compare them to our observed data, right? Because we want to, given the samples that we draw from the posterior, if we simulate them, they should reproduce the observed data. And the fourth one, also very important, is the calibration check. Because we have a full posterior, we have all the uncertainty estimates, and these uncertainty estimates, they have to follow some statistical guarantees, like the confidence intervals, they have to be calibrated statistically. And there are some checks, some indirect checks, that without actually having access to the true posterior, we can say whether the confidence intervals are well calibrated. And if they are not, then something is wrong. Okay. I will not go through this because I want us to work on the second notebook, and we only have 20 minutes left. So let's just jump to the second notebook. So number 2, diagnostics. So everyone please open this notebook. And then, let's see. We take our example, and we don't have to train again. We can just load the trained density estimator from file. I hope this worked for you. If not, the saved objects are in the repository, so you can just load them from file. You don't have to train. And I would say that let's keep this to false. So at the moment we are using this kind of bad approximation with the reduced summary steps, and we go through these 4 steps of diagnostics. So let's take again 10 minutes to work through this notebook. And in this notebook, there's actually an exercise for you, so you're not just executing the cells, but the step number 3. It would be cool if you just do it yourself. And it's straightforward because it's really similar to so the step 3 is the posterior predictive check, and it's really similar to the prior predictive check. Just that we don't simulate from the prior, but we simulate from the posterior. And then we visualize the results. that's something you have to do yourself. But everything else is just execute and just look at the code, what's happening, and raise your hand if there are any questions.
So you said that the prior predictive checks allows us to check that our simulator is not doing something wrong, but it's not a guarantee that it's actually not in the real world. There might still be a discrepancy between the simulator and the real world, and in this case, we would not necessarily be able to detect it via this kind of checks.
Yeah, so the question is whether the prior predictive check really can ensure that the simulator is well specified. And there's no guarantee, but at least if we sample on the prior and then simulate with the simulator, and if we look at the distribution and compare to the observed data, if the observed data is within this distribution, then at least we're not completely off. But of course, the simulator will never be like the exact data generating process in nature. It's always an approximation.
And also, you only check marginal, like the fact that you say that the observed data lie within the distribution is only for the marginal distribution of each parameters.
Yeah, that's a good point. Yeah.
High dimensionality with.
So let's quickly look at this.
Most of the time, I think the prior distribution you use independent variables, you have no correlation structure.
Yeah. So we only look at the marginals. Yeah. So now, if we look at this predictive check, we see the red lines are nicely within the prior predicted distribution. So it looks nice, but you're right. If there was some correlation structure, then we would not see this. We might miss something here. So if we look at the full prior predictive, the data might actually lie not within this distribution. Yeah, this can happen.
And does the posterior predictive check can detect a problem with the simulator?
Yeah, usually the neural network will just not work. So this might be fine, and then we try to do inference. So we train on simulations, and then we apply it to observed data, and then the posterior looks completely like weird, or the posterior predictors are completely off, even though the training worked fine and so on. So that's usually a sign.
Just using the Doppler to see.
Yeah. And there are also more advanced methods to check for model misspecification. That's really an ongoing research topic in SPI, because of course that's a difficult problem.
Just some of these structures that we observe here, like areas, because our observed data is within those distributions, right?
Mm-hmm.
Why, for example, we see such a big peak at 0, or why, the deer kurtosis distribution it's like bimodal.
Yeah.
One very far from the other.
Yeah. I think that's because, it's a prior distribution, so it's just a uniform prior on the entire space, and we kind of randomly forming random combinations of all the parameters, and or the differential equation parameters. And the differential equation, these combinations could be kind of like a stiff problem for the differential equation. So the dynamics might be completely unrealistic and creating extreme cases. That doesn't make sense. So it's really because we are sampling the entire space, and there could be the log curvature, the system of two differential equation. It can really generate extreme data as well.
Okay, so it's not necessarily something to worry about, because maybe we just sampled in very weird places, right?
Yeah. I think there are many combinations of parameters for the local Terra that just don't make sense physically or like biologically speaking, but we're not caring about this because we have a uniform prior here. We're not taking this into account. So actually,
okay, so it's kind of tells us something, right? That actually we should fix the prior to take it into account.
Yeah, we could try to design a better prior given our knowledge about ecology. Yeah. I cannot ignore this here. It's a really good point. But also the power of SBI is, of Bayesian inference is, if we now later look at the posterior predictive, it will look way better, right? Because we were able to constrain, given the data, we can constrain the parameters and kind of zoom into the regions that make sense. Sorry?
So you're not that sensitive to the choice of the prior.
Yeah, in that sense, yeah, we're not so sensitive. Okay, I see that we only have 10 minutes left, so I will also go ahead and go over this notebook together. Just go over these 4 different steps. Step 1, we already discussed. The prior predicted check looks fine because the red line is always kind of within this distribution. The next check is the loss curves. They also look kind of good. So there are no extreme peaks or like no catastrophic forgetting or so. And the next step is the exercise, which we have a solution here. So we just do the check from above, but now with posterior. And here we can see that's already much better. There's still some kind of uncertainty around this, but we are using the reduced sets of summary stats, so it makes sense that it's not optimal, or there's kind of difference between some parameters and some data dimensions. And the last check, it's the calibration check. And this will actually take some time because here the idea is that we repeat the inference many times. So we generate a test set of, say, 100 or 200 simulated observed data points for which we know the ground truth parameters. And then we perform inference for those, and we check the confidence interval of, so for each confidence interval, say for the 90% confidence interval, we check among these 100 inference steps or inference repetitions, how many times does the true parameter lie within the posterior, and it should match the confidence level, right? So for the 90% confidence interval, it should lie 90% of the times inside this interval, and the other 10% should lie outside. And we do this for all the different intervals, for 5, 10, 15, and so on. And this should always match. So we should obtain like a uniform distribution or like a diagonal CDF for the confidence intervals. And that's kind of what simulation-based calibration does. And we can see this. So let me do the other form of the plot. I find this more intuitive. So if we do this for every step of confidence, we see that it nicely matches. So right, for the 10%, we have 10% of the cases and so on. So we have this diagonal in the CDF. So the uncertainties of the posterior are well calibrated.
Could you explain this graph? I don't understand what it means. So that the graph equals to the others actually.
Yeah, so we...
What's the rank?
The rank, it's if we perform inference and we have the observed data, and we also have the true parameter underlying this data, and now we have the posterior, and we just look at the rank of the true parameter in the posterior, so the percentile in the posterior, and we do this many times, and for a good calibration, this number, like the number of times the true parameter lies inside the interval has to match the confidence interval. And this is just one way to visualize this. We compare, for every confidence interval, we look how many times it lies within. And if this matches, then we see this nice staircase. Like it's an empirical cumulative distribution. But if it's not well calibrated, then we would see some divergence from this diagonal line.
There is a bit of divergence.
Yeah, it's a bit off. Yeah. And we can also, this is just a visual way to see it. We can also perform some statistical tests. So we do some Kolmogorov-Smirnov test for uniformity and so on. And then we can see that actually the p-values are below like some alpha value, and then we actually can see that this is not perfectly uniform. It's actually an issue, and it also matches our setup because the summary statistics that we have been using are not optimal. So now if we went back and do the whole thing again with the more informative statistics, so if we set this to true and run the whole thing again, it will be better. Okay.
That shouldn't be well calibrated even if we have bad summary statistics or less informative summary statistics.
That's again a good point, because in principle, if the procedure is too broad, this doesn't. We might still pass the calibration check, but it doesn't have to, right? So it's at least in like empirically, I saw that for the less informative summary stats, the calibration was worse also. Yeah, but it's again a good point, because these calibration checks, maybe that's something I should mention also. These calibration checks, they work with the uncertainties of the distribution. So if we just pass the prior, everything would be perfect, because all the prior is well calibrated. So we will see perfect calibration. So it always has to be used in conjunction with the predictive check. So we should always use the calibration check together with the predictive check, because if we use the prior as our posterior, then we would directly fail the predictive check, because the prior is just not informed. Okay. In the interest of time, we have to wrap up already. So let's go back to the slides. And we have another recap. And as always, time is there's too little time. Exercise 3 we have to drop. But fortunately, this is all online on GitHub. So you can, if you're interested, you can go ahead and try out different simulators. So we have like a Bohr-Thor example from physics, like really simple, just a toy example, and also this epidemic model, sequential infected recovered model, that has been used during the COVID-19 pandemic a lot, so to give all these estimate of the current infection rates and so on. And this problem we can also solve with SPI. And this is kind of a template notebook number 3 where you can try this out. And just quickly, so today we just covered this neural posterior estimation method, MPE, but there are other methods in the SPI universe. There's neural likelihood estimation, where the idea, like the machine learning methods behind this are really similar, but we just, instead of learning the posterior, we learn the likelihood of the simulator. And then once we have the likelihood, we can just do standard Bayesian inference methods, like MCMC, variation inference, and so on. There's also another method called neural ratio estimation that learns the ratio of the joint and the likelihood to evidence ratio. And then we can also do MCMC, but also do things like model comparison and so on. And there's also this idea to perform sequential inference. So if we have really complex, or like a really large, high-dimensional posterior, or like parameter space, and we have one particular observation that we care about, then we can run inference with MPE once, and then do multiple rounds of inference. And in each round, we use to generate new training data, we don't use the prior, but we use the posterior estimate that we got from the first round or from the previous round. We're kind of zooming in into the region that we care about. And this is called sequential MPE. And there are different variants of that. But can be more simulation efficient, but we use this amortization property because we are zooming in onto one observation, and then if we have a new observation, we would have to do the training again. And there are more methods. There are now, like this year or last year, there have been some foundation models for tabular data, so large language models trained on tabular data. We can apply this to MPE, and we kind of get training-free MPE, which is kind of impressive, right? So you don't have to perform training. You just give it the observation, and it will do the inference for you. It kind of works.
How is it possible? Because it's not a normalizing flow.
Yeah, you have to. So the paper, they have to do some output layer tricks on the language model to make sure it's a proper distribution. But it uses autoregressive sampling to ensure that it's a proper density that you get. And there will be a talk tomorrow on NLE and Pyro. So how we can use neural likelihood estimation together with Pyro to perform hierarchical inference. This tomorrow morning in this room. And there are really impressive, really nice applications of SBI in different research domains. And of course, there's a big, now like getting bigger SBI community. This is a photo from this year's SBI hackathon in Tübingen. And if you are interested, I really encourage you to get involved. It's a really nice crowd. And it's really interesting, like really cutting edge machine learning methods and also really interesting applications. And yes, there's the SBI package that we have been using for all the tutorials. There's an SBI documentation on the website with lots of tutorials to get started with. And really cool, good timing. Today we published on arXiv a tutorial paper on SBI. So this is really a practical guide for, if you're not familiar with Bayesian inference or SBI, then this will explain everything in detail using examples and like good practice. And yeah, as I said, you're really welcome to join this community. There's a Discord server, GitHub discussions, and the materials will be online on GitHub, so it's all public. And I really would ask you to give feedback for the tutorial. So you can either scan the link now or just click on the link here. And yeah, just give a short feedback. That would be really helpful. And with that, we're done. Almost in time. Thanks a lot for being here. Thanks a lot for your questions and attention. And I hope this was helpful for you, and I hope you will be using SBI at some point. Hi. It can work without GPU. You can do it on CPU. That's a project.
Separately go through the documentation and try to implement some of the some lists.
simulate the same